resonance helping it out, and so then there's no stabilization to drive the reaction, so this will not leave. So just like this carbon has acidic hydrogens, this carbon does not. This carbon can do with decarboxylation, this carbon cannot because of electron overlap. So one of the key things to realize about this decarboxylation, it only works if your bond that's leaving, that's connected to the carboxylic acid, is overlapping with the pi star orbital of the carbonyl, so those electrons can just quickly jump into the empty orbital. My wife's probably laughing somewhere. She was a scholar athlete for track doing long jump and triple jump. And so my 2-foot jump, or however far that was, she's probably shaking her head for some reason. And she doesn't know why. But once again, in order to do a decarboxylation, we have to have electron overlap with the empty of the pi star orbital in order for it to happen. So this is not that different than needing overlap with a sigma star orbital in an E2 elimination, right? With an E2 elimination, you need your hydrogen to be 180 degrees antiperiplanar to the leaving group, so that the base, so these electrons can jump into the anti-binding orbital and kick out the leaving group. Very similar to that idea. Fair analogy, I think. So, as far as chapter 18 is concerned, that is the majority of the carbonyl chemistry. The last part of chapter 18 is pretty much the best way to teach it is to say ditto. And by that, this chemistry works for any electron withdrawal group. Whether it be a nitro group, a nitrile, and so on and so forth. The major things are nitro groups, nitriles. Sulfonates. Pretty much any electron withdrawing group that's got a pi system for resonance. These molecules often have pKa's roughly the 20 region. And the reason is the same reason as carbonyls, and that's it's got resonance. So just to show you, for a nitro group, if we take the hydrogen alpha to a nitro group, we can take the lone pairs of electrons, and just as before, resonate them into the nitro group in a very similar manner to what we did with the enolate. Like so. And now we can take an electrophile. Any electrophile, someone throw me an electrophile out. Not a carbonyl, because that's the next chapter. Cl2. Nice one. So we can take an electrophile like Cl2, and just as before, the enolate-like species we made will attack Cl2, now giving us our alpha functionalized compound. So this is true for each of these. I won't draw reactions, but I will draw the resonance stabilized anion, just so you guys see. Yeah.
Isn't that breaking the octet rule with the nitrogen? What is that?
Oh, thank you. Is that better? I drew the arrow. I just didn't draw the bond moving. Force of habit. Just the same thing with nitriles. Right. So this is an sp3 carbon. What's the hybridization of this carbon now? So sp3, this is a sp2 because it's a lone pair of electrons adjacent to a pi system. So it becomes sp2. So we can resonate these electrons into the nitrile system. Like so. So I'll let you guys do this one for yourself, but this is really, this case is really similar to phenolate. Minus charge can go into both carbonyls. So the take-home message is, if I can ask a tricky question that's just the typical enolate mechanism, but I might have a nitro group, or a sulfonate, and a nitrile. And just remember, those are acidic hydrogens that act just like nitrile, act just like enolates. And you can treat them just like enolates. And I give you a big ditto for every reaction we talked about. For instance, how acidic do you think one of these hydrogens adjacent to a nitro group and a nitro group is basically? Nitro, nitrile, alpha hydrogen. How acidic? About 10, give or take. So the chemistry is very, very homologous. So focus on enolates and carbonyls, but be wary that anything you do with an enolate or a carbonyl, you can do with a nitrile or a nitro group or a sulfonate, so on and so forth. So be wary. So that really now brings us to chapter 19. And I have the chapter 19 notes. I don't remember if I put them up or not. Did I put the chapter 19 notes up? I'll double check. They'll be up this afternoon if they're not up already. So chapter 19 deals with enolates plus carbonyls as the electrophiles. The first two reactions we're going to go about is the mechanism of an enolate plus an ester. So enolate plus ester, what's going to give us is a diketone. Now, obviously, I'll go through the mechanism in more detail shortly, but it's generally the idea that an enolate attacks the carbonyl to give a tetrahedyl intermediate, which kicks back down to kick out MEO minus. But here's something that's a key point for replacing. So we kick out MEO minus, and we have this alpha hydrogen to two carbonyls. Well, what's going to happen to this hydrogen pretty quickly? they're going to be deprotonated, right? And I'll describe it more next lecture, but this deprotonation event drives the equilibrium, just like for the saponification, the deprotonation of the acid drives equilibrium. So this is a Claisen, and I'll write Claisen in red. Alright? Conversely, the other reaction we're going to focus on is an Algal reaction, which is the reaction of an enolate plus a aldehyde or ketone. Alright? In this mechanism, it's actually much simpler, because it's the enolate attacks the carbonyl, the other carbonyl. And in red, I'll draw the bond that forms. And it gives us this molecule with an alcohol that's on the carbon alpha beta, on the carbon beta to it, yes.
Sorry, did you mean to move that on the where you have Claisen on top there are two hydrogens? Did you mean to move that electron to that bond after you got that hydrogen?
Like so, is that better? Yeah. That was just error pushing, not as precise. Thanks for pointing that out. And so the Algal reaction will give us a product of bond protonation that's got a ketone and an alcohol. So that Al and aldol is for the alcohol. The thing with aldols, though, is you can isolate this. But if you're not careful, let's say you did this under acidic conditions, you can form the enol. And if we're under acidic conditions, we can actually protonate the alcohol. And what happens if we form this? We can kick off water. So now we have a ketone with a double bond. Alright, so again, this is just an overview of what we'll be going over in the first part. And so we'll talk about the mechanism more. But again, so ketone, enolate plus aldehyde gives us aldol. So aldehyde alcohol, there's a product got an alcohol in it. So this is an aldol. And under some conditions, the aldol doesn't stop at the aldol product, which I'm boxing. It actually goes all the way to this unsaturated ketone. This is ketone with a conjugated double bond to it. And in that case, we call this an aldol condensation. And those are really the three reactions we're going to talk about this week. And stop at the exact, yeah.
What happens to the hydrogen under that aldol?
Oh, proton transfer. Again, I wasn't doing the mechanism in depth, I just wanted to give you a flavor of what the chemistry actually looks like. So, take home message from this little 10-minute field. Aldehyde plus ester is Claisen, gives us a product like this. Aldehyde plus aldehyde plus enolate gives us aldol. You have to separate it like this or this, depending on your conditions.